right, here we go. Welcome everyone to the next lesson. We're looking at work some more. Try really hard not to make any puns. I'll work really hard at it. Get it? Yeah, we're going to look at work and how it transfers to become kinetic energy, which is, of course, the work energy theorem in action again, right? Anytime you have energy transferring from one form to another, it's called the work energy theorem. Basically, the idea is work just transfers from one form to another. We're going to see in the next lesson about the idea of conservation of energy and how you're not really creating energy anywhere. You're just transferring it from one form to another, right? So as a starting question here, if you want to press pause and give it a try, we have this situation where we have a 5 kilogram object pushed to the left 10 meters. It's constant velocity, an applied force of 30 newtons of friction against. I guess it has a force against it. That's word kind of bad, but we have an applied force and it's against friction, right? So determine the work done by the applied force, determine the work done by the friction force, and describe the total energy of the object as it is pushed. So let's look at that. So since it has constant velocity, we're not getting any extra kinetic energy. Since we're not lifting it, it's not getting any gravitational potential energy. And so, the work done is obviously the 10, the applied force of the 30 newtons, right, times the 10. So it's doing 300 joules of work on the system. And since we're at constant velocity, we know the acceleration is 0, and the net force is 0, and so on. Net force is the sum of all the forces. So it's just the applied force and the friction force. And so if we subtract the applied force on both sides, we know the friction force is 30 newtons in the opposite direction. And so we have this negative 30 times 10 gives us a negative 30. So that's the work done by friction, negative 300. Even though these aren't vectors, it's kind of awkward where we say, well, there's still signs to do with this though, right? Because you can have energy adding the system or subtracting from the system, right? So we're adding energy to the system, but friction's constantly taking that energy back out. And so the total energy of the system is staying the same, right? 0 joules. Total energy of the system essentially is 0 joules in the end. I guess we could say the change in the total energy is 0, right? But you can tell we're adding 300, but 300 is going out just as quick, right? Second part of this, if you want to pause and try it, is what would happen if there wasn't any friction, right? So in that situation, you'd have a net force of 30 newtons, so you'd have acceleration, and so you'd have, an acceleration of 6 meters per second squared. So it would be getting kinetic energy. So we can do the calculations for that. We've got initial velocity of 0, an acceleration of 6, and a displacement of 10. If you pick the uniform acceleration equation, you end up calculating the final velocity would be 10.95. Well, that 10.95 meters per second must really mean or be the same as or embody or whatever 300 joules, right? Because that's how much energy went into the system, how much work was done. So that's what this opening question here kind of leads us to this topic of kinetic energy. We're going to be able to come back and calculate based on the kinetic energy equation, the official one, that, if we can calculate that the velocity really would be 10.95 if you have 300 joules of kinetic energy. Okay, so we'll come full circle in this one. We're able to calculate the speed this way. We'll be able to calculate the speed using energy concepts as well. So this is using acceleration, uniform acceleration concepts. And shortly we'll be doing getting that same number by energy concepts. Okay. So here we go, kinetic energy and using the work energy theorem, of course, because we're transferring energy. So EK is our symbol for that. It's energy due to motion. You can consider that potential energy as well, because something that has motion has energy that it can use to do other things, right? Drive a post into the ground or whatever. And so when work is done, we know we're going to be like pushing an object. That's the basic definition, right? So the object accelerates. And so the velocity is increasing. It's gaining kinetic energy. So this is the idea, right? Work done is delta E. It's becoming a delta EK. Okay, that's your work energy theorem. add that word. Where is it? There. Copy and paste right there. Just to make sure you don't forget the idea that that's what the work energy theorem is. So energy changing from one form to another. So if we're looking at the equation for kinetic energy, what should we start with? Well, I think it would make sense to start with how something is gaining or getting kinetic energy. And that's, of course, by a force on it, accelerating it, as we saw in the opening question. And we know that forces that do work as they apply over a distance. So we have work equals force times distance as your starting. Oh boy, delete, but okay, it wasn't deleting anything. Good. So work done is the logical place to start, because that's how we're getting kinetic energy, right? So we have work done is a change in energy. What's F? Well, F equals ma, of course, right? Newton's second law. And so we have F equals ma, and we have what? We have the kinetic energy then is going to be ma times delta V, right? This part here, if we're looking at relative to 0 joules, right? It's just EK, but otherwise it's like a delta EK, I guess, right? But it's if we're relative to 0, then we can just say EK. So your kinetic energy is obviously just relative to a velocity of 0 in that reference frame, just as a standard issue, kind of like we did with the gravity version, right? Just relative to the floor or relative to the lowest point in your reference frame or whatever. Okay, so this delta D, let's analyze that a little farther, right? When we're pushing on something, it's accelerating. So we have this concept here of uniform acceleration. We could use equations, or we could use the graph method because it's pretty easy. So we have 1/2 of the base times the height to get the area. That's your displacement. And so really we have this nice easy result here of 1/2 delta T delta V. So this equation, kinetic energy, becomes the ma times the 1/2 of delta T delta V. Okay? So we're developing. We're actually just reasoning out what the logical equation for kinetic energy must be. At this point, we can say, well, acceleration equals delta V over delta T. We're not quite crossing that thing out yet. But acceleration equals delta V over delta T. So the delta V's cancel out. The delta T's even cancel out. And, sorry, not delta V's. The idea of it being a change, I apologize. The idea of being a change is not relevant if we're saying relative to 0. Okay, the delta T's cancel out. I just was getting rid of the delta concept from that in that section. So since we have this velocity v1 is 0 business going on, right? I should color code that to make it a little easier to see what I did and why. So those deltas, all this stuff, let's make those be like orange or something so it stands out, right? We don't have to have the delta symbol anymore. So really that's a v times a v, which of course is a v squared. We have a 1/2 concept, and we have a mass. So really we have an equation of 1/2 mv squared. Okay, and that's your kinetic energy equation. Units for that, if you're checking it out, we'd have kilograms, and we'd have meters squared and seconds squared, which if you remember, that is the units for energy, right? That's the so-called joule, and named after Mr. Joule, James Joule, something like that. Yeah. So if we went back to that opening question, right? If we look at, if we do 300 joules of work, then we have 300 joules equals this 1/2 of the mass was 5 kilograms. We just solve for V, right? Divide both sides by 5, multiply both sides by 2, and then of course we have to take the square root of both sides. And guess what? 10.95, right? Just like we found. So this is getting the final velocity based on energy concepts, as it says here. Okay, so if a question on a test or a quiz, whatever, says on an assessment of some sort, says to determine the answer with uniform acceleration concepts, that's like the opening question we originally did. And then if it says, okay, now do that based on energy concepts, this is what it means, right? Using the energy concept directly. So yeah, energy concepts often give a much easier and shorter method to get answers, right? This seems kind of simpler, where we didn't have to know all these uniform acceleration equations and so on. Just use the amount of work done to get the answer directly. Okay. So typical equation type work for this, right? If you have a 3-variable equation, I'll give you 2 of them. You can solve for the third, right? So we can solve for, we can find out how much kinetic energy there is. We can ask what the velocity would be. We can ask what the mass would be. If you're given 2 of them, you can find the other one, right? So plug in the 10 and the 5 and calculate. In this case, plug in the 5 and the 125. So the 5 for the mass and the 125 for the kinetic energy. Just solve for the speed or the velocity or whatever. So notice here, what do I have here? Oh yeah. We're gonna talk about that soon, but I'm just not sure if that's what I have here. I don't know if it's a good. Oh yeah, it's not a good comparison necessarily because we're just looking at half the mass. But anyways, because of the squareds, you're not sure, right? So the velocity needed to have the same amount of. That's why I just didn't read that first, right? Velocity needed to have the same amount of kinetic energy if it's half as much mass. Well, if you put a half in here, when you're looking at what speed, because you're rooting things, it's not what you're going to think, right? A lot of people might have guessed it'd be double the speed in order to have, the same amount of energy, but it's not because of that square in that equation, the pesky square. Okay, so this is another example of that. So if the velocity doubles, okay, what's the increase in kinetic energy if the velocity doubles? Well, you're going to have a factor of 2 in there to double the velocity. 2v squared is the same as 2 squared times v squared, which is the same as v squared times 2 squared. So basically, we can move that 2 squared outside. You have a 1/2 mv squared, which is just regular old kinetic energy, right? So basically, we have 4 times the kinetic energy. It shows that the kinetic energy is actually bigger by a factor of 4 when you double your velocity, right? So it's always really going to be the square of the increase factor, right? So think about that in terms of highway safety, right? If you're going faster, you have more energy than, say, if you go 10% faster. Well, you're going to be more dangerous, if you will. You have more energy in your system than you think. You're like, oh, I'm only going twice as fast. An example of twice as fast is just easier to talk about, right? So I'm only going twice as fast. So it's a 40 zone and I'm going 80. Don't do it. You're going to get in trouble. But you know what I mean. The kind of energy you have in a collision is 4 times as much, or it's a square times as much as what you think, right? So this is why they have this kind of campaign to help people understand that speed kills. Speed is dangerous. It's more dangerous than you think. The other thing that comes up is that if you're looking at a delta v, like a change in velocity that's not from 0, you can't just slap delta v into that thing. 1/2 m delta v squared is not an equation that is true always, and that's because v squared minus v squared minus v1 squared minus v2 squared minus v1 squared. How am I supposed to be? Oh, sorry. I'm just having trouble seeing things here because I have these sub superscripts by accident instead of. Wow, I really botched that. Give me a second here. That's supposed to be v final minus v initial, right? So, not notice that. Surprised it didn't come up in previous years. So v2 minus v1 squared is not the same thing as v2 squared. So I need to put this in there. I can make that be. Yeah, it's not the same as v2 squared minus v1 squared. It's just not how numbers work. Yeah. So that's not the same. So you need instead to do the final kinetic energy minus the initial kinetic energy and get the values, like that. You can't combine it. So any example you want to do here can show that, right? If you did say 10, they had a final velocity of 10, an initial velocity of like 2, right? If you did 10 take away 2 squared, you'll see that that's not the same as 10 squared take away 2 squared, right? This is just 8 squared is 64, and this is 100 take away 4. This is 96, right? So it's just that same mathematical non-equivalence or difference leads to incorrect physics answers. Okay, and so this is something that needs to be said. We tend to think that mass doesn't matter because we've seen that all objects fall at the same rate due to gravity, right? But mass matters for energy. Even it doesn't make what we said not true. Okay, so if you have a light object falling and a heavy object falling, they end up with the same velocity. Sure, that's fine. But a heavy object with a big velocity embodies a lot more energy than a small object, a light object, a small mass object, getting that exact same velocity, right? And we can see it in action here too, where if we have, say, 10 newtons acting over 2 meters, that's 20 joules. Well, what's the result of that? Well, it's either going to be a fast result or a slow result, right? Because if you had a small mass, then that's going to be lots of acceleration, right? And so you're going to end up going fast, but it's a small mass, so that's not a lot of energy. Or it's a heavy object, large mass, and so it's going to be small acceleration. It's going to be going slow, but again, these are the same amounts of energy. Okay, so each of these, they're both 20 joules, and that's okay. That's not a contradiction. So I've had to be careful in the past, and correct things in the past where I'd ask questions about energy, and I'd kind of forget to throw mass in there because mass is sometimes it often doesn't matter, right? If you're just falling due to gravity. So I'd be like, oh yeah, I got to give you the mass in that case. Yeah, so I think that's about it. Obviously here you just give you the mass and velocity and ask what's the kinetic energy. Easy peasy, right? 1 and 2 are find the kinetic energy and determine the kinetic energy and determine the mass. I think there's probably one about determining the velocity somewhere. I'm not sure if I threw one of those in there or not. I put 8 to 10 as being optional because they're kind of repeats, and then 8 and 9 are repeats, and then 10 is involving uniform acceleration work. So if you feel you need practice with that old concept, then do that one as well, of course, or working towards the exam, make sure to do it, I would say. Yeah, so hopefully that works for you. And in the textbook, if you want to look over the material, the digital textbook that's on the site, 214 to 227 is where the material is. I didn't bother leaving the original page and number references here for this, because read through the textbook portion if you need extra info. And yeah, I'm always available for help as well, of course. So thanks for watching, and have a good rest of your day.